All right, last section here, chapter 8, improper integrals. So an improper integral, there's two different ways that this can come about. The first way is whenever you're doing an integral where one of your limits goes to infinity. So let's look at some of those first. So just some quick definitions here. If f of x is continuous on some interval starting at a and going to infinity, then we can integrate from a to infinity over f of x dx. Okay, now the way that we do that is we take the limit as b goes to infinity, integral from a to b f of x dx. All right, so anytime you have an infinity as either the lower limit or the upper limit, do this limit trick. It's not really a trick, it's the definition for it. Take the limit as b goes to infinity, and then replacing the infinity with b instead. Go through the whole process, find the antiderivative, plug the b minus plugging the a in, but then after all of that, then take the limit as b goes to infinity. Okay, so same stuff. If f of x is continuous, but now the other way around, this time we have the integral from negative infinity to b, f of x dx. To do this one, take the limit as a goes to negative infinity, integral a to b, f of x dx. The last kind of question you'll see is whenever you have an integral from negative infinity to positive infinity. For this one, what you're going to do is you're going to break it up. Find some location c where you can integrate from negative infinity to c over the function, plus integrating from c to infinity over the function. This is the additive rule for integrals that allows us to do that. I usually choose 0 for the c, but choose something that makes the most sense. Okay, one little thing to write down before we get into some examples. I just turned the page, didn't even think about it. If the limit is finite, then we say the improper integral converges. All right, so in other words, when we do this and we take that limit, if the limit comes out to be a number, we say it converges. If it blows up to infinity or negative infinity, we say it diverges. All right, so let's look at an example. Let's do the integral from 1 to infinity, natural log x over x squared. Okay, so before we jump into the integral, we're going to rewrite this as the limit as b goes to infinity, integral 1 to b natural log x over x squared dx. Okay, now you want to go through your mind of chapter 8, all the different techniques that we've done and how to handle this one. This is going to be an integration by parts, so we need to create a u and a dv. We're going to let the u be the natural log x, the dv we're going to let be the 1 over x squared dx. Then the du would be the derivative of natural log, which is 1 over x, and v is the antiderivative of dv, negative 1 over x. Remember that for integration by parts, it's uv minus integral v du. So we're going to multiply the u and the v together, negative 1 over x natural log x, minus the integral of v times du, which would be negative 1 over x squared dx. Okay, go ahead and find the excuse me, the antiderivative here. So these double negatives are going to be positive, and then the antiderivative of 1 over x squared is negative 1 over x. Okay, so, I forgot my natural log x here, sorry. Negative 1 over x natural log x is canceled out. This just comes straight down. Okay, so just to rewrite that because it looks awful. Negative 1 over x natural log x minus 1 over x. We're evaluating this from 1 to b, and then all the way on the outside, we still need to take the limit as b goes to infinity. If I plug b into all of this, I'm going to get negative 1 over b, natural log b, minus 1 over b. that minus plugging 1 into all of this. If I plug 1 into here, I just get negative 1, but then the natural log of 1 is 0, minus 1. Okay, now we need to figure out what this limit is as b goes to infinity. We'll worry about this one in a minute because that one's a little bit difficult. Let's look at this one. If I plug infinity in for the b here in the denominator, that just goes to 0. So this we need to talk about. If I plug b into infinity, the fraction goes to 0, but the natural log of infinity is infinity. So this is going to be one of those situations where I have infinity on top and infinity on the bottom. This is L'Hopital's rule. Okay, so just kind of over in scratch paper, we're trying to figure out the limit as b goes to infinity of negative natural log b over b. With L'Hopital's rule, we take the derivative of the top and the bottom separately. Natural log b has derivative 1 over b. The b in the denominator has derivative 1. So really we're trying to figure out what the limit as 1 over b, negative 1 over b as the b goes to infinity. This of course just goes to 0. So this term also goes to 0. The only thing we have left is this negative of negative 1. So that means that that integral up top, the integral natural log x over x squared from 1 to infinity, has answer 1. Which means it converges. Okay, cool. So I hope you can kind of see how cool that is. Just to kind of show you on the calculator what's going on here before we look at another example. If I can get it to come over. So let me just graph this. We had natural log x divided by x squared. Okay, and we'll graph. All right, so remember we were only caring about the integral from 1 to infinity. This is a little bit above the x-axis, and it was kind of hard to tell there, but it is slightly. We can change the window size here to really show that. So let's just go from 1 to, I don't know, just keep it maybe at 20 or something like that. We don't need the y's to go up so high. Let's go from negative 1 to 1. Okay, so here's our graph. Natural log x over x squared. As we go out to infinity, notice that the function gets closer and closer and closer to 0. It never actually reaches 0, but it gets infinitesimally close. So this integral from 1 to infinity, or this area under the curve, really does come out to be that finite number of 1. I hope you can see how cool that is, that we have an area that stretches out to infinity, and even though it stretches out to infinity, it still has that finite area to it. Okay, let's look at maybe one more example here, and then we'll see, or we'll look at the other kind of integral techniques here. Okay, great. All right, so maybe this example here, let's do the integral from negative infinity to infinity of dx over 1 plus x squared. Okay, remember when you have infinity on both the lower and the upper limit, what you want to do is to choose a c so that you can break it down into two separate integrals. I'll choose 0. Let's do negative infinity to 0 of dx over 1 plus x squared, plus the integral from 0 to infinity, dx over 1 plus x squared. Okay, for both of these, we're going to do that limit. So we're going to do the limit. I'm going to go from a going to negative infinity, and it'll be the integral from a to 0 dx over 1 plus x squared. Plus a separate limit, the limit as b goes to positive infinity, integral from 0 to b of dx over 1 plus x squared. All right, now we need to find antiderivatives. So these we're both going to get from that integration table. I forget if it's number 18 or number 19. Both of these has tangent inverse as its antiderivative. So the limit as a goes to negative infinity of tangent inverse of x from a to 0, plus the limit as b goes to positive infinity of tangent inverse of x, this time from 0 to b. All right, so let's plug that stuff in. If I plug 0 into tangent inverse of 0 is just 0, so that's nothing. So really this is going to be the limit as a goes to infinity, negative infinity, of negative tangent inverse of A. Right? That's because we plugged 0 in and got 0, minus plugging A in and we get negative tangent inverse of A. That's going to be plus the limit as B goes to infinity. If I plug B in, I just get tangent inverse of B, minus, if I plug 0 in, I get nothing. All right, now we need to talk about what the limit is as A goes to negative infinity inside of tangent inverse. So this isn't something I would expect you guys to get right away, although maybe after a little while of thinking about it, it's not too bad. Let's think about what the tangent function does in the graph. The tangent function does this. The inverse tangent would then do the rotation of that. It would do this. So we need to figure out what tangent inverse of negative infinity is. Well, as my x value goes out to negative infinity, I'm approaching this asymptote, which corresponds to this asymptote. All right, so this asymptote here corresponds to this asymptote here. We just need the values. The asymptotes for tangent is at the pi over 2's. So this asymptote is at negative pi over 2. This asymptote is at positive pi over 2. Which means that when I plug negative infinity into tangent inverse, it's approaching negative pi over 2. I still have this negative out in front, but then tangent inverse of negative infinity, negative pi over 2. That's going to be plus over here. Now we need to figure out what tangent inverse of positive infinity is. Well, as x goes to positive infinity, on the tangent inverse graph, it approaches this asymptote, which corresponds to positive pi over 2. So we end up with negative of negative pi over 2 going to positive pi over 2. These two things add up just to be pi. Great. So here we go. The function 1 over 1 plus x squared from negative infinity to infinity has the area of pi. Just again to graph it real quick, we'll change it back to a regular thing as well. So 1 over 1 plus x squared. Again, we're going to change it back to Zoom standard. So here's our graph. It's just a little hump right there in the middle. But again, right, notice that from negative infinity to infinity, they both approach 0, so they do die down, and we have this little bit of area here. Now this area does stretch out to infinity, it just gets infinitesimally small. What I want you to see how cool this is that we do not have a circle anywhere, right? But still, the area under this graph comes out to be pi as the total area. Fascinating to me. Okay, so in the second video, we're going to look at the other kind of improper integrals.